Hello everybody, my name is Jorge, I'm from the University of Central Florida. This is some of our students. We're here with Dr. Sebastian Lobo-Guerrero, who is visiting us here. And we're here to show you some of our projects. So this one is our FDOT Florida DOT funded project about auger cast piles. As you can see, we have like a physical model test. So we're installing auger cast piles in a scale environment.
And we are at the top on a humongous cube, right? That's the ground surface down there. That's the ladder that we use. Huge cube full of sand. And what are you going to do with this?
Actually, our experiment is going to be like one of top scale physical experiments, physical model tests. So
excellent.
We hope that we have some kinds of insight about the behavior of auger cast pile. So basically, the main purpose of our research is to investigate the spacing effect on the ACP embedded into synthetic limestone, because we believe that the spacing effect is going to be decreased when the ACP pile is constructed into the synthetic limestone. So basically, through our experiment, we try to investigate the effect of spacing on the actual behavior of the pile. So that's what we are doing right now, and yeah, we hope we have great experimental results from our experiments.
Awesome. So tell me the process, how you construct it.
So we are following trying to simulate the construction procedure of an auger cast pile, like drilling with a continuous fly auger, also like hollow stem, where we're pumping, if you can see here, we're pumping our grout inside of the hollow stem as we remove it.
So you drill it, right? I mean, you rotate it, drilling, go down.
And then as we retract the auger, we're pumping the grout at the same time as we retract the auger.
And it's kind of going to look like the one.
Yeah, so this one is a specimen that we were just like kind of like showing and doing forensics on this specimen installed with this methodology. And you can see like hopefully all the piles are going to look like this.
And then what do we do? We construct it?
We have some sensors. So we have strain gauges. We also have some thermal sensors provided by DFI actually.
Yes. Talk about that. Tell me what I like to hear.
Yeah, so we got some sensors also from DFI to install in our piles to check the
thermal temperature.
Yeah, thermal temperature sensors to
distribution along the piles. So
yeah,
we can see DFI tried to make a correlation between the thermal temperature and the pile diameter. So they send us the sensor to measure the temperature along the pile, so that, and then after the experiment we are going to measure the diameter of the pile. So then we are going to send that data to the DFI so that they can do some statistical analysis about the temperature and the pile diameter. So yeah,
excellent.
It's called PI thermal pile integration.
Yeah, the PAT.
Yeah,
PI.
Yeah, so we still trying to find how to install the thermal sensor into our pile. So like probably with after like this test, after the first test, we can see how we can install the thermal sensor to our pile.
Awesome. Well, that sounds pretty cool. So I guess this one is already constructed, right? We're going to wait until it cures, and then we put the load and we fail it, and that's going to be another video later on, right, with the results of the test. Well, thank you very much, and let's fail this thing. Bye.
How's it going, everybody? Matt Glisson. I am the Director of Technical Activities with the Deep Foundations Institute. I've been in the role 2 years as of yesterday. And it's a great role. I'm enjoying it a lot. I started my career, I went to Marquette University thinking that I would go into environmental engineering. Found out that chemistry and I don't exactly mix too well, so I made a change into just broader civil engineering. Met my now wife at Marquette University, and we were going to go to Charlottesville, Virginia, and so I was looking for a job in the Virginia area, particularly Charlottesville if I could find it. I got an offer with Schnabel Engineering out of their Charlottesville office. It was the one job that I found that wouldn't mean traveling to Richmond or Blacksburg or DC, commuting those kinds of distances, so I took it. So that's how I wound up in the geotechnical community. So it was really, I kind of fell into it. I enjoyed the one class that I had as an undergrad that got into soil mechanics and foundation design, the intro to foundation design that you take. But from there, it was a small office. I wore many hats like many of you have done, right? So I could have been out behind a drill rig all day long, come back into the office, bring in all the samples, and find out no one had pulled the concrete samples for that day that needed to be broken. Be there for another hour and a half capping them, and because we didn't have neoprene caps, we were using sulfur. So enough of that, right? But anyway, I fell into the position. I really enjoyed the different experiences that I got as a new graduate, out in the field, in the office, analyzing, calculating, designing. It was a small office. I got that's mine and you're not yours. Don't drink that one. I really enjoyed the opportunity that I had to develop some templates and some things that helped move that office forward a little bit. And from there, following my wife around with what she was doing, I wound up in Minneapolis and hooked on with a consulting firm there, Braun Intertech, and did that for 17 years. And as part of going to Braun Intertech, at the time that they hired me, they were looking for someone to supplement their deep foundation group. And I distinctly remember as I was meeting with them and talking with them, I said, I don't want to get pigeonholed into just deep foundations. I had enjoyed being the generalist geotechnical engineer up to that point. I didn't want to exclusively do deep foundations at that time. I'm pretty sure I was at Braun Intertech for less than a year when somebody said, hey, you should join Deep Foundations Institute. It'll really help you, advance your career, learn about the industry a little bit more. And so now 17 years, no, where are we, to 2024. So 19 years later, all I have done since then is specialize in deep foundations. So totally did not fulfill my initial intent of not being pigeonholed, but it turns out I was wrong. I did want to be pigeonholed. I did want to become a specialist in deep foundations, and DFI is part of why I wanted to become specialized or stay in and get more and more specialized in it. Learning the things that I learned and attending the committee meetings and the conferences, and meeting the people that just absolutely love deep foundations and this industry and helping the industry forward. And so from there, being a part of DFI as a member, seeing all the stuff that the committees were doing, it probably took me about 8-9 years to really get engaged in a committee where I was raising my hand. I was confident with where I was in my career and what I knew, that, you know what, I'm just going to say, yeah, I can do that, even if I didn't know how I was going to do it, and volunteering for a committee thing. But I'd seen our previous director of technical activities, Mary Ellen Large, doing this role, and I kind of thought it was pretty cool what she was doing and how she was helping the industry and helping DFI. And when I first found out about Mary Ellen doing that, I didn't realize that she was an actual DFI staff person. I thought she was one of DFI's members and she was doing it as a volunteer, but I thought it was cool. When I found out she was volunteering, I'm like, yeah, no, that's not for me. That's not my career. I don't want to work for a nonprofit. Fast forward 11, 12 years, and I was looking for a change in my career. I'd reached a point at where I was probably as far as I was going to go. At Braun Intertech, I wasn't going to be satisfied there longer term, but I might have been, right? I don't know. Things change all the time. But I needed a change for me and what I was doing, and I decided that I needed that change. And within a couple of weeks of deciding that, I was at DFI's conference in, I believe it was Las Vegas that year, and Teresa Engler, our executive director, announced that Mary Ellen was going to be leaving at the end of the month and that they were going to be looking for someone to replace her. And I approached Mary Ellen and said, I might be interested in taking that position over. And I didn't know what would come of it, right? I didn't know if I was going to be, I didn't know how many people were going to be applying for it. I didn't know if it was exactly what I wanted to do, or if I was going to be, exploring other options within the industry. Interviews, negotiations went along, and they made an offer. DFI made an offer. Was it an offer I couldn't refuse? No. But it was an offer that was right for me at that time and that stage in my career, and what was right for me in my situation. What I really like about being in this position, besides, there's a lot of things that I really like about being in this position. The top of the list, though, is absolutely that I am getting to give back to the industry that has supported me for 20 years and helped me to grow and become the engineer that I have become. I guess I still am. I wanted to say past tense was, but I think I still am an engineer at heart. Even though I'm not doing engineering on a day-to-day basis, I'm still using that engineering degree, that engineering knowledge, in the interactions and the communications that I have with our committees and what they're wanting to do. But being able to give to the community, look at the challenges of how do we get that next generation into our industry, how do we help them to become as passionate about deep foundations as we all are, is a really exciting place to be. And it's not just that aspect of it. We've got committees that are developing standards of practice or standard guidelines and specifications for segments of our industry that have never had that. In developing those guidelines, we are going to move them from here to here. We're moving them up 3 levels at one shot, not just incremental advances, right? The marginalized kind of advances, the ones that just happen organically. These are purposeful, intentional. Let's make what we do and how we do it better for all, with the lens not of personal gain or even personal company gain, but because this is going to help all of us advance. It's going to save resources. It's going to lead to more economical designs. It's going to lead to more sustainable use of resources, whatever it happens to be. All of those things in many cases. That's the exciting part of being in this position for me. Yes, there's the personal side of it, of getting to meet all of our 500 or so committee members and interacting with them and working with them. So DFI has a lot to offer the industry. I think we are looking at, as we're working on our strategic plan right now, we are looking at what are the concrete goals of how we're going to be helping the industry so succinctly in the next 3 or 4 years, 5 years, if you will. And those are some fantastic things that we've got going on. So join in, find the role that you've got for DFI and how we can help you and how you can contribute to our industry.
My name's Ryan Allin. I am Vice President here at Pile Dynamics. We're here in our lobby, and we're basically giving you a 2-minute tour of the history of Pile Dynamics. Looking at this, we have various different pieces of equipment from across our history, going all the way back to the original PDA. Of course, this is just one component of the original PDA. When they were doing the initial research, it actually filled up the back of a van. But of course, as time goes on, these components get smaller, more efficient and powerful. So we get to the late 70s, early 80s. These now become kind of more compact systems. They don't quite fill up a full van, but they still probably require about 8 transit cases to do your testing.
And all these was PDA, right, on the left?
All these is PDA right here. And then, of course, kind of our big kind of leap forward was the PAK system. This was the first self-contained unit where you kind of had this briefcase that you can now walk on site and collect all of your data. And that brings us up to our current version, the 8G over here. which is now like a little tablet version, larger screen, touch screen. Going up a little bit further, we have our SPT analyzer, that's for energy calibrations, and then we get over on this side, this is all for integrity testing. So we have our pile integrity testing, our low strain system, which, going all the way back to 1991, was using a touch screen as an interface. So you think of today with our iPads, that was well ahead of the curve. We have our thermal integrity profiler, which basically has data loggers and a main unit right there. Our cross-hole system that you see right here. And then going over here on the far side, there's early on developments of looking at crane booms. Nothing, we don't make this anymore, but it basically was an angle analyzer so they could monitor the angle in the crane boom. Of course, that's all built into cranes these days. A static load testing system. You may not know, PDI has a full-fledged static load testing system that basically has smart sensors that can determine what type of gauge it is. And then for the driven pile market, we have our saxometer. This has been a widely used tool across the entire industry for monitoring hammer strokes on diesel hammers. And then some of our new systems down here, just the tablets. We have our squid system, which is checking for debris layer thickness in drill shafts, and then our sidewall measurement system, our shape system.
And you always have to have a DFI magazine, right? I see
And
it right there.
the DFI magazine, that's right. Yeah.
All right. Well, no, thank you very much for taking us through the Wall of Fame and all the preliminary models. And yeah, awesome.
Yeah.
Looking forward to a whole tour.
Thank you for
Thank
joining.
you. Bye.
Michael Bennett. I'm a geotechnical PE with Gannett Fleming in Valley Forge, Pennsylvania, and I enjoy studying and collecting pieces from geotech history in my spare time. Sometimes I also pick up pieces from civil engineering history more generally so I can better understand and contextualize the origins of geotech. So today I'll discuss the heritage of civil engineering in the United States railroading, along with some global context, and I'll share a few items tied to that, like this badly deformed railroad spike. Now, so much of good engineering is innovation and invention, and it's often said, of course, that necessity is the mother of invention. Now, what often drives necessity, in turn, is what Karl Marx once called the dull compulsion of economic relations, and railroad civil engineering is a perfect example of that. For instance, in the early 1800s, the UK was in the driver's seat, or perhaps the engineer's seat, in developing a lot of the basics of railroading technology, such as signaling systems. For instance, this lantern. However, U.S. railroad civil engineers realized fairly quickly that just importing the latest developments from overseas wouldn't cut it, because the United States' larger size, lower population density, and more rugged terrain meant that American railroads needed much lower operating costs per mile than their European counterparts did just to stay afloat. So American railroad civvies got busy putting their Yankee ingenuity to good use. In 1854, the Pennsylvania Railroad's civil engineers opened the Horseshoe Curve in western Pennsylvania to surmount the Appalachian Mountains. And then in 1862, construction of the Transcontinental Railroad between Omaha, Nebraska, and Sacramento, California began, and it was finished in just 7 years. And that line remains a civil engineering marvel. It involves 1,800 miles of track over towering bridges, mammoth cuts and fills, and 15 tunnels through the Sierra Nevada mountains. And by 1900, there were 5 such lines spanning the western continental United States. And those, along with the denser network of eastern rail routes, fueled the Industrial Revolution in America. The Iron Triangle of coal and steel and railroads helped unite the U.S. and propelled its transformation into an economic and international superpower. And during those years, railroad civil engineers pioneered all sorts of theoretical and practical innovations in the field. Papers such as building bridges upon well foundations on the Madras Railway and reconstruction and enlargement of Cork Run Rail Tunnel filled U.S. and global civil engineering journals. The Cooper Load series for the design of railroad bridges introduced in the Transactions of ASCE in 1894, was among the first universal design codes in U.S. civil engineering practice. The Swedish State Railways Commission performed the world's first in-depth geotechnical study from 1914 to 1922, following a series of deadly slide-induced derailments. In fact, that study is where the term geotechnical originated. And a number of railroad projects played host to professional excursions. In 1914, ASCE members near Scranton, Pennsylvania, visited the Lackawanna Railroad's Tunkhannock Viaduct, 240 feet high, the world's largest concrete structure at the time, while it was still being built. This booklet is actually a souvenir from that excursion. And by that time, U.S. railroads were really at the zenith of their golden age. American track mileage peaked in 1916 at over 250,000 miles. That's enough track to reach the moon and still construct 4 transcontinental lines. But nothing lasts forever. Even as U.S. railroads basked in their glory years, the first airplanes took flight, the first Model Ts rolled off assembly lines, and a shift in transportation modes began. That became particularly noticeable after World War I, when it was research on highway and not railroad civil engineering that led to many early geotechnical advances. This while our discipline was still getting established. Now, the Great Depression and World War II slowed those changes and temporarily kept railroads in the lead, but projects such as the first section of the Pennsylvania Turnpike clearly showed where things were headed. And after World War II, the U.S. automotive age really shifted into high gear. At that point, the tides turned harshly against American railroads. Now, that was not a universal trend, because during that span, Japan and South Korea and many nations in Western Europe built robust high-speed rail networks, but the U.S. government invested its transportation resources in the interstate system. Now, that system is undeniably a positive, but it nonetheless subsidized the automotive, trucking, and oil industries, and it made private automobile travel and long-distance freight trucking viable and cheaper alternatives to passenger and freight rail. Now, passenger train service in the U.S. dwindled to almost nothing during the 1960s, and a lot of faltering railroads entered panicked and ill-advised mergers that failed. And the biggest and most spectacular of those failures was that of the Penn Central Railroad, which the contemporary press covered at great length in books such as this. And Penn Central's bankruptcy in 1970 represented the largest in American history up to that time. Now, that collapse finally got the U.S. government to take action on American railroads' decline. Congress created Amtrak to nationalize passenger rail service, and also took over Northeast U.S. freight rail by creating Conrail. And over the following decade, Washington built on that by passing prudent bipartisan deregulation that helped stabilize the health of U.S. freight railroads. And today, those lines are turning record profits. For instance, Conrail started turning a profit in the 1980s. It was privatized at that time, and in the late 1990s, it was purchased by its competitors. And that's really in contrast to American passenger train service, which has remained underused, underfunded, and I'd argue underappreciated. Multiple attempts to bring high-speed rail to U.S. shores have fizzled, most notably in California and in Texas. But still, the proud history of U.S. railroading, which was fueled in large part by the brilliance and foresight of U.S. railroad civil engineers, indicates that with adequate funding and political will, this situation can be changed. Thank you all so much for joining me today. Until next time, I'm Michael Bennett, signing off for DFI.